Hello, everyone, and welcome to today's webinar, Pressurized Steam Electrolysis and a Vision for Sustainable E-Fuels. I'm Shannon Reed, the Director of Community Engagement for the Electrochemical Society. Before we get started, I'd like to go over a few items so you know how to participate in today's events. You may have joined the presentation using your computer speaker system by default. If you would prefer to join via a different audio option, please select your microphone and audio settings to change the audio options. You'll also have the opportunity to submit text questions to today's presenter by typing your questions into the questions pane of the control panel. You may send in your questions at any time during the presentation. We will collect the questions and do our best to respond to them during the Q&A session after the presentation with time permitting. To begin, I'd like to thank the ECS Pacific Northwest Section and Dr. Dustin McLartym, both of whom made today's webinar possible. And mark your calendars, the 242nd ECS meeting is taking place in Atlanta, Georgia from October 9th through the 13th. Registration is now open and early registration ends on September 12th. The ECST manuscript submission site will be open until July 15th. For more information about these meetings, visit electrochem.org/meetings, and I look forward to seeing you at a future ECS meeting. Now, for a few points of the Pacific Northwest Section news. Mitchell Kaiser has received the 2022 ECS Pacific Northwest Section Electrochemistry Student Award. The section established the award in 2021 to recognize promising young engineers and scientists pursuing PhDs in electrochemical engineering and applied electrochemistry, and to encourage recipients to continue careers in these fields. The winner, Mitchell, will receive a $1,000 prize. So congratulate Mitchell on his achievement. Additionally, the Pacific Northwest section has established the ECS Pacific Northwest Section Electrochemistry Research Award, and the application deadline is July 15th. The award recognizes excellence in electrochemistry and solid-state science and technology research, and is given annually to a candidate who is independent scientist or engineer working in Washington, Oregon, or Idaho in the fields of electrochemical science and technology and/or solid-state science. It is based on outstanding achievements in either electrochemical science or solid-state science and technology, and acknowledges the excellence of the candidate's publications and/or technical contributions to these fields. ECS membership is a requirement, and candidates must be nominated. Self-nominations are also encouraged. The winner of this prize receives a certificate of recognition and a $1,000 prize. Again, the deadline to apply is July 15th, 2022. Now, I'd like to introduce today's speaker. Dr. Dustin McLartym is an assistant professor in the School of Mechanical and Materials Engineering at Washington State University. He holds both a master's and doctor of philosophy degree in mechanical engineering from the University of California, Irvine, and a Bachelor of Science degree in aerospace engineering from the University of Florida. Dr. McLartym studies high-temperature fuel cells and the dynamics and controls of advanced microgrids. The research expands upon previous systems integration experience garnered in Irvine, California, Boulder, Colorado, Birmingham, United Kingdom, and Morgantown, West Virginia. Involved in research for clean energy systems, Dr. McLartym has worked with industry partners and national labs to develop systems integration solutions and novel electrochemical power concepts. Originally from DeLand, Florida, Dr. McLartym is a lifelong competitive swimmer who has represented the U.S. national team at international competitions and has also served as a professional surf lifesaver in both Daytona Beach and Huntington Beach. In today's webinar, you'll learn about pressurized operation of solid oxide cells, trade-offs in performance and economics, EIS testings of vanadium-doped zirconia electrodes, and testing facilities available for collaboration at Washington State University. Again, we welcome your questions. Send them at any time during the webinar using the Q&A functionality, and our presenter will answer as many of them after the presentation as possible and moderated by the Pacific Northwest Section Chair, Dr. Jay Zhao. Now, I'll turn today's webinar over to Dr. Dustin McLartym. Dr. McLartym, take it away.
Thank you. Good afternoon or morning, everyone. I'm very pleased to be here to share some thoughts with you. Hopefully, some of them are of interest. Okay, share. Here we go. All right. Great. So I'm going to be talking about electrolysis, particularly my emphasis in my lab. I've been working on pressurized systems, going back to working on pressurized fuel cells for fuel cell gas turbine hybrids. So my talk today is I first want to introduce you, if you aren't aware of DOE's hydrogen Earthshot. Their statements about it have some controversial statements, but at least the funding that is coming down the pipeline is really great for our field of electrochemistry and fuel synthesis. Then I'm going to go through some details about why I think pressurized electrolysis is actually the future and how we're going to achieve that Earthshot. And there's obviously some benefits to it and some distinct challenges of going to really high pressure. And so I'm going to talk about my vision here at WSU and how we're going to address those challenges, specifically with this new material development, a whole category really of vanadium codope materials that we're working with. And then finally, I'll pitch all of you on joining us in trying to develop a National Electrofuel Center here at Washington, led by Washington State, but it'll be a consortium of universities where we can really do fundamental research as well as industrial commercialized research in this area as well. So again, last summer, DOE launched several, over the year, they've launched several of these Earthshots. The very first one they announced was this goal to reduce the cost of hydrogen by 80% so that it was $1 per kilogram by the end of the decade. And along with that overarching goal, they released a statement that if the hydrogen shot goals are achieved, you'll see a 5-fold increase in clean hydrogen use. We'll see a 16% reduction in CO2 emissions by 2050 and 140 billion in revenue and 700,000 jobs by 2030. All wonderful aspirational goals. I question a few of them. They've got some issues. My first question is, where can I get $5 per kilogram hydrogen today? If they're going to reduce it 80% to $1, that means it must be $5 today. I would love to be able to buy $5 kilogram hydrogen. It's just not available in many places. And then, are they really expecting all this by 2030? If they're suggesting that we're going to have 140 billion in revenues, well, last year, 2 years ago now, the revenue was 900 million. And industrial research folks expect it to grow to around 2.5 or 3 billion by the end of the decade, but we need to be averaging 17 billion to get there in 8 years. So that might be a bit of a stretch. And then I was really confused by this idea that we're going to see a 5-fold increase in hydrogen use, and we're going to reduce the cost by a factor of 5. So wouldn't that mean we have the exact same revenue we have today? And I'm not sure if we're actually going to be able to hire 100,000 folks in this field every year, because I don't know where we're going to train 100,000 people in hydrogen every year. But that is one of the goals of our center, is to do that workforce development, especially here in the Northwest, where we are definitely leaders in this area. So some of the specifics of their statement were a little bit of a stretch, but the overarching goal of $1 per kilogram green hydrogen, there's a lot to that. So let's see if that's even reasonable or feasible. Well, clean energy, everyone looks at California for leadership normally. And if we start with a typical PEM electrolyzer you can buy off the market today, the most efficient ones are advertising a nameplate efficiency of 55 kilowatt hours of electricity for every kilogram of hydrogen produced. If we look at California's average retail electricity price, that comes just the input, the feedstock energy is over $7 a kilogram. Okay, well, California is going to be a stretch to reach this goal. Let's look at a business-friendly Texas, where you can actually get, because of their deregulated energy market, you can subscribe to 100% solar electric rate. For, I think this is a 5-year locked-in fixed price. You can get 12.5 cents per kilowatt hour delivered to your house. Well, that's still almost $7 of energy cost per kilogram of hydrogen. So that's going to be a tough sell. Well, let's look at where we are here in the Northwest, where we have the cleanest, greenest energy in the nation, and it's cheap too. Our state energy mix is 80% carbon-free and costs on average 4 cents for industrial consumers. If you go and put your Bitcoin mining rig right at the dam today, you're going to pay around just under 3 cents, and that works out to a remarkable $1.58 per kilogram of input. So we're getting closer, and we have a huge advantage over Texas and California. So this is why Washington is really talking about being a leader in this area of electrofuels and hydrogen. But it's still not $1. So we have to do something more to get to $1. So let's look at the cheapest energy in the world, and we got to cut out the middleman. We have to cut out the grid, because the grid's going to charge you 2 or 3 cents just to get it from the farm to your facility. So looking just at solar farms, the average of the 25 largest solar farms PPAs built last year was $27 a megawatt hour. That's pretty good. The cheapest ever built, claimed, is a very large solar park in Saudi Arabia that came in at $13 a megawatt hour. They didn't have to pay or lease the land at all, so that's really just the facility and infrastructure cost. And they have great solar potential there. So it's going to be hard to get to $13 here in the Northwest, but let's imagine we can get to 20, which works out to 2 cents a kilowatt hour. Using existing PEM electrolyzer technology, you're just over $1 on your feedstock cost. Pretty close. But if we want to go a little farther, we could talk about solid oxide electrolyzers. And these have the potential to be down around 40 kilowatt hours per kilogram, much more efficient use of the electricity. So now we're at 80 cents of input cost, your variable cost, and that leaves a bit of a margin for your upfront capital costs. So let's break down that design matrix or cost matrix of between your operational costs and your fixed costs. What I've done here is sort of 4 axes on these charts. The left chart is showing you the operational cost to produce that hydrogen based off of your input electricity cost and how much electricity you use. So very simply, we want to be somewhere around 80 cents. You can see the trade-off there between the electricity cost and your consumption. The right graph is focused on your fixed costs. I put on the bottom axis the cost per kilogram hour of capacity, and on the vertical axis, how many tons of hydrogen over the lifetime of that system. And then I tried to make the right-hand axis just a translation to something easier to understand. So if we're talking about trying to get to this $1 per kilogram target, we probably want to be somewhere on the 80-cent line, which means we need to be around 45 kilowatt hours per kilogram. And that translates to operating an electrolyzer somewhere around 1.5 volts. On the system lifespan, we have to really assume some type of degradation and some end-of-life condition. So if we assume we're going to operate at fixed voltage and there's a linear degradation in the conductivity of our membrane, you're going to have a sort of 1/x production curve over its lifespan. In this example, I just assumed end of life meant you were producing 25% of your start of life, which works out that curve to an average of 46% of its initial capacity over its lifespan. So if you make those quick assumptions, you can translate these tons of kilogram over its lifespan to something we can relate to in years. And we get somewhere around 8 to 10 years is what we need. So we need a cheap system, we need it to last 8 to 10 years, and we need it to be quite efficient if we're going to hit these targets. So these are ambitious things. The bottom axis, if you're used to different price things, if you know, optimistic goals and targets are to get to $100 per kilowatt of capacity. That's sort of this value 5 that the graph starts at. Where we are today with solid oxide systems is probably the right side of this graph, where it's about $1,000 per kilowatt of capacity. and that's maybe lasting 5 years. So we're talking $2.5, $3 of the hydrogen cost is just a capital cost. Today's PEM systems are probably contributing somewhere between $1 and $1.50 to the overall cost of the hydrogen. We're somewhere right in the middle of this chart, and we just have to move upward on the fan to get to the 20-cent curve. So quite ambitious targets, but I do think these are achievable. So imagine we are successful in producing $1 per kilogram hydrogen. What are we going to do with it? Well, a lot of talk, especially in our region, injecting it into the pipeline, decarbonizing that natural gas system. Realistically, upper limits are about 20%. They're targeting maybe a 10% regulatory maximum initially, but let's average that and say we could get up to about 15% of the volume in our natural gas system as hydrogen. Unfortunately, that only works out to about 7% of the energy content, since hydrogen is a rather not dense gas. And will people actually pay a premium for a fuel that's 7% less carbon in the fuel? Not particularly. So you're going to be paid pennies for this fuel content. So it's not a really valuable use of hydrogen, and it can't actually, while yes, displacing 7% of our natural gas would be a huge amount of carbon reduction net, it's not likely the first place that hydrogen is going. What's done today, mostly moving it around California, is we liquefy it. It costs somewhere between $5 and $8 for that extra, capital equipment for the cryogenic system, all the trucks and the distribution system moving it around. So for every kilogram, we're adding $5 to $8 cost, and that's why it's $15 per kilogram at the pump in California. It's $7 of fuel cost, $8 to get it to the pump. So that's going to be difficult. We could compress it and truck it. It's a lot more efficient to compress it. And the trucks are a little cheaper, but we can only carry about 900 kilograms on the most advanced tube trailers. So if we actually achieve $1 per kilogram, you're gonna use an entire semi-truck lorry to move $900 of goods. I think I put $900 of goods in my trunk every time I go to the supermarket these days. So it's just not a viable means of getting hydrogen moved around. Now we could build a dedicated pipeline network, and that's part of most of the proposals for this hydrogen hub, Northwest Hydrogen Hub, is we'll have some dedicated hydrogen distribution system, and that works for big industrial consumers and specific applications. It's not going to address transportation everywhere or residential energy consumption in any way. Hopefully we can produce a lot of it on site, and that just gets rid of the problem of moving it around. And then the final way is, well, what if we just took that beautiful clean hydrogen and attached it to some carbon, and we can move it around in the energy networks we already have? They're cheap, everyone knows how to use them, they're safe. So this is something I want to dive into a little farther. So if you're going to take hydrogen and make it into a liquid fuel or natural gas, we need to attach some carbon. We want to make it carbon neutral. So you got to get some green carbon somewhere. There are definitely places where there's carbon capture happening at fossil fuel plants, but we need a sort of universal solution, and we want to shut down all those plants anyway. So we need a solution like direct air capture. The largest examples of this today are approaching $100 per ton of CO2 captured. The DOE has set another one of their Earth shots, is a targeting of $60 per ton. And that works out here to 53 cents per gallon of gasoline equivalent. So if you're starting from $1 per kilogram, and a kilogram of hydrogen is roughly the energy content of a gallon of gasoline, and we're adding here 53 cents of carbon to it, well, my question is, would you rather be in the business of selling $1 per kilogram green hydrogen, or would you rather sell $1.50 per gallon green gasoline, or even $2 or $2.50 green gasoline that you're going to make a lot more money that way and also have a much bigger impact in terms of reducing carbon. So I'm fully supportive of DOE's shot to get to $1 per kilogram hydrogen, but I don't believe achieving that will launch a hydrogen revolution in terms of transitioning everything that we possibly can to hydrogen. I think it'll actually open the door to electrofuels in general and non-fossil fuels, but direct replacements for our fossil fuels that are carbon neutral. So that's where I want to focus my efforts, and that's where we're trying to propose a center that would focus on this as well. So with that background on where I think electrolysis is going, I want to focus on pressurized electrolysis and talk about some of the benefits and challenges with that. So the clear benefits are, if you can do your electrolysis at pressure, that means you can pressurize the liquid water and then produce your gas, rather than producing a gas at atmospheric pressure and having to use a hydrogen or gaseous compressor that's expensive, unreliable, and inefficient. When you go to quite high pressure, you can actually get better thermal energy recovery just because of the thermodynamic properties of the fluids we're dealing with, and I'll show that in a moment. You can get better integration with the thermal chemistry. So if you want to do methanation or ammonia synthesis, these things need to be done at high pressure. So if you can produce your hydrogen at pressure and go right into the reactor that's doing this thermal chemistry, you can combine the thermal, make your electrolysis exothermic, and if you have an endothermic reaction, that it can be paired with that. Pressurized electrolysis is great for direct integration with our different storage opportunities, right into pipelines or your end use. Imagine a filling station that looks just like an electric supercharger, where the hydrogen is made on demand at the pressure as it goes into the tank. That's going to be more effective than trucking hydrogen around and having this liquid hydrogen storage that needs to be boiled off and recompressed in a very complicated fueling station. The other benefit of pressurization I'm going to talk about and show examples of is microchannels in your reactor. So when you pressurize something, you densify the gases, you can actually have much smaller flow channels, which means you can shrink your whole system where the electrochemistry is happening. And once you get to large production scales of anything, what you really pay for is mass. So if you can cut mass out of the system, you're almost always cutting costs out of the system. So the challenges associated with pressurization are always the same. It's sealing the thing. Seals are bedeviling when you go to high pressure. So that is a major challenge. Then we also have thermodynamics working against us in some cases, and we get primarily at the oxide electrode, you see a lot of material degradation for most of the strontium containing perovskites onto a YSC cell. Now, low temperature electrolyzers, PEM alkaline, they've demonstrated pressurized operation. They're pretty reliable. You can buy systems today operating at 30 bar, 200 bar. And so I'm going to compare a little bit to that as the baseline of how could we achieve 30 atmospheres of pressurization with a high temperature electrolysis. Now I'm going to present some results of an analysis that a student worked on, and it's focused on this generic system. I'm going to detail it a little bit here. The premise is you have one liquid water pump that's doing all of the pressurization. It goes into this heat recovery system where it's recovering as much exhaust heat as possible. And you have two potential places for supplemental heat addition. That could be electric heating or heat recovery from another process. And then I really want to start by highlighting this idea of an ejector here right before you go into your electrolysis stack. And the ejector is allowing you to recirculate some of your high temperature gases, your steam and hydrogen, back through the system, because most of the material sets on the steam side don't want 100% humidity. They want some amount of hydrogen in there to sustain the electrode. Now, looking at the ejector, if your background is fuel cells like me, you'd say, well, that's going to be a bad system. The ejectors make things worse. And this is really true in fuel cells. Rolls-Royce had a great design. They really worked on these ejectors. I had some collaboration with them when I was at UC Irvine. And the best you can really do when you use ejectors for recirculation rather than a blower, you're going to pay a penalty for that. And you're going to pay about 10 to 20% of the cell output, because you had to pre-compress all of this hot air going into the system above the operating pressure to really drive that recirculation with the ejector. This is not going to be an issue with electrolyzers, because you're able to do liquid pumping, which is far more efficient at getting to pressure than gaseous compression. It just takes that much less work. And you also end up with a very favorable density ratio between your motive fluid, which in this case, we have steam as the motive fluid and a mixture of steam and hydrogen as the entrained fluid, which is a lower density. So you get this very favorable density ratio, which improves the efficiency of an ejector, and the fact that you're not compressing a gas to provide the motive pumping power. So even in the worst case scenarios, the ejectors in a high pressure electrolyzer is still going to account for well under 1% of the total electric input to the electrolyzer. So it's a nearly negligible impact having that injector, which is nice, because now we have a solid state, part that will never break and can handle the high temperatures very easily. So let's talk about the exhaust heat recovery. From a systems perspective, this is really what drives the overall efficiency of the electrolyzer system. Yes, we have the electrochemistry happening. That's key. But from a systems perspective, we really need to capture as much of that exhaust energy as possible to have high efficiency. What I'm trying to show with these charts, the one on the left is the difference between the liquid water going into the system that needs to be boiled into a steam before it reaches the high temperature electrolyzer, and then the return gases, which is mostly hydrogen with some moisture in it and a secondary stream of the oxygen you produce. Combine both of those and send them through your heat recovery system. And so the supply water is in the black lines, and the return exhaust gas is the red at different pressures. And you can see as you go to higher and higher pressure, you get to supercritical steam, you actually need less heat addition. So this difference at the top between the red exhaust and the black supply, that's how much supplemental heat you need to add to the system. So you get a benefit when you go to high pressure. The other thing I wanted to point out is when you have more and more humidity in your exhaust system, that's extra water you supply to the system that you didn't split and is coming out of the system, and you're trying to recover that energy. When you have a substantial portion of exhaust humidity, you really run into this pinch point where these lines cross, and that doesn't work in a heat exchanger, because you always need your hot fluid to be hotter than your cold fluid. The heat won't go the other way. So when we do the system design, we really have to focus on this pinch point analysis to make sure it's a feasible amount of heat recovery. And again, going to a high pressure system reduces those pinch point limitations. Sorry, and these were 5% exhaust humidity and 33% exhaust humidity on those two charts. So let me show you a single example of how we would do this pinch analysis. So I have that heat recovery system design here on the left, where at the bottom on this blue line, your fresh water comes in, it recovers some waste heat, and then it goes to this first boiling steam generating heater, and then it goes through a second heat recovery heat exchanger for the high temperature exhaust, and then it may or may not need this secondary heater as well. So for one particular condition, this is just showing how we try to, we need the red line to stay above the blue line within 10 degrees, whatever our minimum pinch point is for the heat exchanger design. And we need to define the amount of heating we would need from these two heaters to get the supply water up to the appropriate temperature without these lines crossing. So you can see we've identified how much heat we need to put into the pinch heater and how much supplemental heat up here at the top end we would need. So we can do this analysis for all sorts of operating conditions and really start to understand how we should run a high pressure, high temperature electrolyzer. So that brings me a little bit to the electrolysis itself and the thermodynamics happening in the water splitting reaction when we go to pressure. We have some benefits, but actually a few drawbacks from a basic fundamental thermodynamics of going to pressure. The orange line here is the thermoneutral voltage. So this is the voltage you could operate your water splitting where you wouldn't be heating up or cooling off your stack. So it's a really good operating condition because you don't need balance of plant doing any cooling or supplemental heating of your stack itself. Now there's always going to be some natural heat loss. So your actual operating thermoneutral voltage is usually a bit above this line just because you have heat loss. Surrounding that orange line is a green band, and this is representing sort of your viable, your sustainable temperature window. So you have fluids flowing through your stack, and they can come in a little bit below your operating temperature and leave a little bit above your operating temperature. So you might be able to tolerate up to 100 degrees difference between the inlet and outlet. And that thermal capacitance gives you a little flexibility in how you operate your system. The more humidity and the more flow, the more recirculation you put through your electrolyzer, the wider this band can be. On the bottom, and in the blue line, I'm showing the reference voltage. And this is the electrochemical potential of the cell. If you were at 50-50 hydrogen and steam, you're going to be right on this line. If you have extra humidity, your open circuit voltage is going to be below that line. If you have very dry hydrogen, your open circuit voltage is going to be above this line. So if you want to operate all the way down to zero current sustainably, you need to expand this green sustainable temperature window wide enough that you actually intersect with your open circuit voltage. So that brings me to, not that chart. The other point I want to make here is that it's a drawback. So there's a slight drawback when you go to pressure because your thermoneutral voltage goes up a little bit, meaning you're going to need a little bit more energy going in for every mole of fuel produced. So that's a slight drawback. The other point I wanted to bring up is the difference between your operating condition and that open circuit voltage. That's your driving voltage potential that's going to influence how much current and how much fuel you're able to make. So you want to expand that as much as possible. And unfortunately, when we go to pressure, this gap closes a little bit. So the yellow line is showing how initially, as you pressurize a little bit, that voltage potential you have drops significantly, but then it levels off and actually begins to increase a little bit towards the end. So it goes from around 240 millivolts down to at really high pressure around 190, 195 millivolts. So it's a little bit of a drop in your voltage potential, but you can recover that by expanding that green operating window and getting to a higher operating voltage. So we put all this together. We put the heat recovery system together, the steam generation, the electrolysis itself, the hydrogen compression, and we get an overall system energy consumption. And so this stack chart is really showing you as a function of voltage, what are the contributions to the overall energy balance. The vast majority is the energy going into the electrochemistry of the water splitting. So following this linear slope here with voltage. Then you have a significant, in the purple here, the amount of heat you need to produce that steam. And then at really low voltage, you actually need that supplemental heater to boost the steam heat, because at these low voltages below the thermoneutral voltage, your electrolyzer would actually be cooling itself So we need to superheat the steam so that steam can provide the extra energy into the electrolysis itself. And then above that, if we were operating at atmospheric pressure, we would have to pay for the energy of compressing that hydrogen, that's shown in the blue. And just as a relative, how significant that hydrogen compression work is. When you go all the way up to 700 bar, which is delivery pressure for vehicles, this 2.5 kilowatt hours per kilogram for hydrogen compression actually increases all the way to almost 7. So it's about 15% of the total. So if we want to produce hydrogen for vehicle fueling, it is going to be massively advantageous to do this with a electrolyzer that can operate at that really high pressure and use a liquid water pump instead. I put on this graph here the ideal operating window, sort of where this green section ends and before this red section begins. So in this operating window, you neither need to have extra supplemental heat going into the stack, and you don't need to cool your stack. So if you operate above, substantially outside that green window that I was showing you, you actually need some sort of secondary fluid to reject heat from the system. Now, PEM electrolyzers use just a water cooling loop. We would need something different in a high temperature electrolyzer, and it means the whole stack gets more complicated, more seals, more flow paths. So you can definitely design a simpler system if you can operate in a window where that's not necessary. The purple section is the heat needed for boiling the water. If you're lucky enough that you have available waste heat or geothermal heat that's at 400 degrees, you could actually displace all of that in a high temperature electrolyzer in a way that you couldn't in a low temperature electrolyzer. So it's another way to reduce the energy consumption by another 10 to 12% if you have readily available waste heat. Right. If you did have that secondary heat transfer fluid in your stack and you were able to move the heat from the stack to actually displace some of that preheating, that has a distinct advantage for you. You can operate at a much higher voltage, meaning more power, more current density, for the same net energy consumption. Because really it's taking some of this red heat that's recoverable from the stack and displacing here this purple section, which is your steam preheating. So you get this wide operating window that is effectively the same efficiency for your hydrogen production. And so that can have a lot of advantages. Within my lab, we refer to this operating condition here as the system thermoneutral. It's really the peak energy that would balance the energy of the whole system. It's not really a thermoneutral voltage for the stack. The stack itself is actually exothermic in this case, but that exothermic energy is being recovered to provide some of the steam boiling. All right, so if you're designing a pressurized system, you have a couple competing goals. You want to maximize your output, the amount of fuel you produce, while also minimizing your energy consumption and retaining some flexibility to go all the way from very low power to very high power. If you're connected to a solar farm, you need to be able to shut down fairly easily. So these three charts are really showing you where the trade-offs are as you try to change the humidity, the exhaust water content, and how much recirculation you have. That's how you can, again, raise or lower that open circuit voltage and expand that viable, sustainable operating window. So I'm showing here sort of an ideal condition is maybe 25 to 30% exhaust water humidity. And that gives you, if you have a high enough flow ratio, this gives you the ability to turn your system all the way down to open circuit voltage and operate at zero power when the sun isn't shining. And through all this, it's fairly efficient. It's under the target 40 kilowatt hours per kilogram. So this would sort of be an ideal way to design your high pressure, high temperature electrolyzer. Okay, so hopefully I've convinced you pressurized electrolysis is a viable and beneficial way to do electrolysis. I want to talk about how we're trying to do it at WSU with our VYZion material. One of our innovations is a new ceramic manufacturing method where we're trying to print three-dimensional geometry with these zirconia-based powders and eliminate all the seals. As I said, seals, that's the challenge. But if we can actually use 3D printing to eliminate all those seals, that would be great. So this was our first prototype. And what this is showing, that's depositing a layer of fugitive material. The white powder there is YSC, which is your typical electrolyte in a high temperature fuel cell. And we can deposit interspersed into that fugitive material that will evaporate out of the assembly during the firing process. So we can leave behind these microchannels for gas routing, and we can do all different layers. So we print a layer, press it, print a layer, press it, and do additive manufacturing in that sense. And we want to produce a design like this. So the picture on the left here, this is a Saint-Gobain design, and they did this via extrusion. They made a slurry, a very thick paste, extruded it with these holes, and then cut it into rectangles and stacked them together before they co-fired it. We want to do the same co-firing, but we want to print the layers with dry powder on top of each other so that we can have all of the gas routing internal to the ceramic part. So in Saint-Gobain's design, they have this ceramic block with holes on all the sides that they then needed face seals on all four sides. So it reduced the amount of seals necessary, but there still were seals, and they were very difficult seals because you had to apply this radial compression rather than just axial compression, which is usually easier to add at high temperature. So we're trying to build this assembly like you see on the right. The other main difference between Saint-Gobain's design and ours is theirs was designed for atmospheric pressure. So they needed decently sized holes for the gases to flow through. So those holes were, I believe, somewhere around 3 to 5 millimeter diameter holes. And if we're going to go to really high pressure, we can take these channels down to 50 or 60 microns. So we've already been able to demonstrate, and in this picture, you're seeing a sample we cut open and put in this SEM, where we were able to produce sub-100 micron channels that were contiguous and unblocked through an entire component. So we're able to do these fine micro features and do it via printing so we can get into really fancy geometry. And the goal here is basically shrink everything down, less mass, 20 times smaller, all with this without any seals, high temperature seals to worry about. We also get into some advantages as we can do this with integrating with methanation and that fuel synthesis. Is we can have multifunctional layers, we can add catalysts. You can imagine 10 layers of electrochemistry that then merge and go into a layer where there's some thermal chemistry happening where carbon comes in and meets up with the hydrogen and some thermal chemistry happens. And then we can integrate the heat transfer between the electrochemistry and the thermal chemistry. So that's where we can start to play around with the design and really think of this as a mini refinery, an entire fuel synthesis refinery in one ceramic brick. So to enable this, we needed all of the materials to be very compatible so that they would co-sinter. And the general perovskites that have been used as electrodes were not viable at high pressure. So we actually found a way to take our normal electrolyte material, YSC, and our goal is to make YSC electrically conductive. And we found that with enough vanadium doping and some secondary dopants that we're also boosting it with, we can get a very stable defect cubic structure that's identical to the electrolyte while having electrical conductivity. So we actually have these components that are co-sintered, and you can't even tell the difference in an image of where the electrode ends and the electrolyte begins. We can do a line scan and see that the vanadium isn't diffusing into the electrolyte. So we can see the barrier layer there, but this is, something that will never ever delaminate at pressure. So that's been a major milestone to show that we could make this material with the property we needed. It remains compatible with the electrolyte, and we can print it and make these micro features inside of it. So that's been our huge milestone, and where we're really taking off with this research. We've been testing in a 10 bar facility that we developed years ago for testing commercial apparatuses up to 3 or 4 kilowatts. So it's a large 12-inch internal diameter that we can work in. But we really wanted to explore this at much higher pressure. So over the past 6 months, we've really built this first of its kind. We're not aware of anything that exists in the world that's like this, but it gives us the ability to test button cells and small stacks up to 2 inches diameter at up to 100 atmospheres. The rig itself is rated for 3,000 psi, so we could go to 200 atmospheres eventually, but the gas bottles we get supplied are around 137 atmospheres, so we really only get about a quarter of the bottle if we're supplying it at 100 atmospheres. So eventually we'll take this even higher pressure, but this has been an enormous challenge to build. But it's very exciting because we're getting some fantastic results that the world's never seen before. So if you have any interest in collaborating on this, feel free to reach out. So I was going to show a bunch of EIS results, but those are hard to dive into, and some of them give away a little bit more than I'm keen to give away at the moment. So these are just some general results of our new material to show that it is viable, we haven't achieved the level of performance from state-of-the-art electrodes, but we're getting closer. So the chart on the upper right is showing that we did exceed 100 milliamps per centimeter squared at 1.4 volts when we pressurized to 9 atmospheres. So still an order of magnitude lower current than we'd like, but this was with a rather thick pellet. This printing method at the moment, we're still making very thick samples. This was about 800 microns thick for the oxygen conduction length. So we see the opportunity to make it 10 times thinner, which should very quickly get us to 10 times more current. So we see the potential there. The other main thing to highlight, we did a test, a 2-week test, and actually during those 2 weeks, it was still improving, still in that initial conditioning phase. So it's not a material that breaks down and degrades really quickly. It's got some longevity to it. We don't know yet if it's going to be the 8 to 10 years we need, but it's got some promise there for durability. So yeah, performance is on its way, durability is on its way, and high pressure is on its way. So with that, I want to conclude with a little pitch. We're putting together a team of academics. It's going to be four or five universities led by WSU, focused on this electrofuel future. So beginning with hydrogen as that initial bridging fuel and the niche applications where hydrogen makes perfect sense, and then building to something that would displace all of our transport fuels, all of the industrial fuels, the fertile industrial ag ammonia, trying to get all of those fuels produced from clean, sustainable energy here in the state of Washington. And it's a big push in conjunction with the Hydrogen Hub proposal from the Department of Commerce. And I think it has a lot of potential for Washington to remain a leader in electrofuels. Anyone that wants to participate and join, please send me a message and we'll find a way to get you incorporated in the center here. With that, I'd like to conclude. Thank you for your time, and I'll be happy to answer any questions.
Great. Thanks, Dr. McLartym. So we've got a bit of a change in the agenda. So Jay had to hop off the call, but I'm going to facilitate the Q&A for us. So audience, please feel free to submit your questions using the Q&A tab on Zoom, on the Zoom control panel. Dr. McLartym, the first question I've got for you is how high pressure is reasonable to do electrolysis?
Good question. Really, it's down to what the material in the system can handle. We have most applications are 20 atmospheres and above. Pipelines are somewhere between 60 and 80 typically. The vehicles we like to fuel, the semi-trucks are generally operating with the cheaper tanks at 350 atmospheres, and the vehicles are more commonly fueled at 700 atmospheres. For the fuel synthesis, ammonia needs 40 or 50. Methanation would want to be somewhere above that to have a substantial driving force for the methanation reaction. So we're targeting 100 in our demonstration, and that really unlocks a lot of these applications, but I see it going up to 500 or 600 if possible.
Got it. And then I know you mentioned a couple times during the presentation regarding, seals at high pressure. So can you talk a little bit more? Have there been any sealing challenges operating at high pressure? What are they?
Yeah, the pressure is one thing. It's the temperature also. So making materials compliant for good seals and durable under high temperature, oxidizing and reducing conditions is a challenge. Glasses are a common approach, and we've done a lot with glasses. We've also, for robustness and just speed and testing in a lab facility, thermoculite, it's a bit more expensive, but it certainly fits the bill in a lab setting. You just have to apply a bit more of a compression force. So when we work with button cells, it's rather simple. Just the swage locks holding the pipes together can provide enough compression force. When we move to larger systems, we have to stack weights or have an external press. So we've mastered these. For atmospheric pressure, it's relatively simple. You just put a hole in your furnace and you can press it from the outside. Pressurized furnaces require a bit more intricate design to be able to apply compression force for your seals at temperature and handle all
that. Okay. And then why have others not pursued high pressure electrolysis?
Well, I probably imagine because it's rather difficult. So I think lots of people see the benefit for it, and definitely all the low temperature electrolysis is moving towards pressurized systems, just because it makes your piping and plumbing system a lot easier on the back end, and usually the application is already at pressure. It's really just been a bedeviling challenge for high temperature solid oxide because of the material set. It doesn't handle pressurization as well.
Okay. It looks like we have another question from the audience. At high pressure, you're showing current density about 7, which seems quite low. Why so?
Let me go back to that. So let's see. So this first chart, I think, was at 750 degrees Celsius, where we exceeded 100 milliamps per centimeter squared on again, a rather thick button cell. Then we threw a different one in for a durability study. And this was the first test. We've done subsequent tests, but this one was done at 650 degrees just to, we wanted to show, especially that it at least had the potential for durability. So we ran it at low temperature where it would survive as long as possible. So the difference here in power density that you're seeing between atmospheric durability tests, which approached 5, and the first one was 750 degrees. So our material is zirconia based, highly temperature dependent. Where that trade-off in lifespan versus operating temperature and performance is, I don't know. So if we can make it thinner, we can get the same power at lower temperature and have it last longer. So that's our manufacturing goal, which is a more mechanical challenge, my wheelhouse of mechanical engineering. And then we can mess around with the compound and then secondary dopants to try and improve the stability at higher and higher temperatures so that we can improve performance that way while retaining durability. So big design space to explore. The tests are not quick and easy and cheap, so there's a lot to do. But we feel with these initial results, and we've got more recent stuff that I'm not ready to show, because we've made progress from these starting points. But this was our first, okay, we prove it works and we prove it can do something, which just needs to improve.
Understood. Thank you. Next question that's up. Are there humidity constraints with the VYZion materials? I know you did speak in regards to having some necessity for humidity for the electrodes in the system. Can you speak to what humidity constraints there might be with the VYZion materials?
Good question. So it does not behave the same as normal YSC. It does, as a powder, it loves water, which has made it very difficult to work with because we've had to build custom dry boxes and dry presses to do everything in a dry environment for the manufacturing. That's been a big challenge. So it's very hydrophilic. It loves water, and that's one of the reasons it actually works better as an electrolyzer than a fuel cell. It really wants to absorb that water onto the reacting surface. So it hasn't shown a need for we've operated with pure water in a way that a typical high temperature electrolyzer cannot operate.
Got it. All right. And then I think we have time for one more question. And this is, again, speaking to the VYZion. Are the VYZion electrodes reversible?
They are. They've worked better as a electrolyzer than as a fuel cell. But we're improving that, and with the latest designs, that's sort of converging. So it likely had issues with the original porosity, but it does seem to be perfectly reversible. We've cycled it back and forth a dozen or 20 times and seen minimal degradation with the cycling. We do know the oxidation state is changing. We can observe that just with the color change, but it does seem to be a reversibility that is not causing a degradation.
Okay, great. And I think that wraps up our Q&A, Dr. McLartym. Thank you. And thanks to everyone who asked a question. I would like to go through just a couple closing slides here. So let me share my screen. And here we go. All right. Awesome. So thank you again, Dr. McLartym, for your presentation today. I know that I am definitely walking away with a couple of things, and I'm not a technical expert or scientist, so some really great insight and questions there. So I appreciate that. We do want to highlight some upcoming additional webinar events that we have with the organization. We know that the Society's monthly webinar series showcases distinguished speakers and members of the ECS community and offers solutions to pressing concerns for scientific researchers. Our next presentation is on June 30th, so this coming Thursday, in partnership with Inago Academy's Dr. Despina Sanadu on how to boost citations with tips for researchers. To learn more or to register, you can visit electrochem.org/webinars. And then we also have another webinar scheduled on July 20th with Dr. Luis Fernando Arenas on flow cells. Again, visit electrochem.org/webinars for more information. And we are accepting future webinar topics. You're more than welcome to email me at shannon.reed@electrochem.org with your ideas. And with that, the recording of today's webinar will be available on the ECS YouTube channel within the next few days. We encourage you to recommend the webinar to your colleagues and share the recording on your social media accounts. Feel free to tag ECS. One last thank you again to Dr. Dustin McLartym and to the ECS Pacific Northwest Section for organizing today's webinar. Thank you to the audience members for joining us. And with that, today's webinar is now over.